Good evening. We're going to continue discussing the basics of electric field. So to begin with, as we had discussed in the previous lectures, charge is a quality of a massive body. So when we say in general, when we are going to say charge, it is shorthand for charged massive body. And it is the ability to cause an electric field in planar. We have discussed what planar means at length in the last lecture number 7. If you have not yet watched that, please do. This planar is not nothingness, it is a physical thing. So like any physical thing, it has extension, so it is extended, and it has qualities or it has properties like electric field. So if I have a charged body or simply charge, it is creating or it is causing, rather than creating, I should say causing. Uh, so this charge Q is causing electric field in its surrounding parts of the planar. And this electric field, which is caused by this charge Q in this planar, has the ability to propagate in the sense that transfer this to the neighboring parts of the planar. And ultimately, if I have another charge, let's call this Q1, if I have another charge Q2, this electric field can give an impetus, or it can move this another charge Q2 based on the proportions of Q1 to Q2. So because this impetus, this movement could either be this way or that way, we call those effects, to include it in mathematics, we call it as negative or positive charges. So the important thing to note here is that this charge is spreading out through the planar, through the electric field. So you can compare this to an incompressible fluid flow by an analogy. Electric field is not really like a fluid flow, but by analogy, if we were to take a source of water at the center and we are spreading it out, if I spread it out at a radius of r, the surface area is 4 pi r square. And if I spread it over 2r, then twice the radius, 2r, then I would have 4 pi times 2r square. So I'm spreading same water over a larger surface area. So the field, the electric field itself, is decreasing as a function of the surface area, or 1 over r square. So electric field is decreasing as 1 over r square, and it is proportional to the amount of charge I have here, Q. So this electric field is Q over r square and spreading out radially outward, right? So that's how we are defining electric field. And before we go into details of Coulomb's law, let's consider one thing here, that when we are talking about plana is a physical thing. That means it's actually composed of parts, and it can be divided into a certain number of actual parts. It is not a mental construct. So you cannot have infinite parts. You have actual number of parts. So what is the smallest part that planar can be divided into? We don't know the answer, but things point out to something called Planck's length, which is essentially square root of h cross g by c cube. This is on the order of 10 to the power minus 35 meters. So that is roughly the order of magnitude, if you will, where the graininess of planar itself becomes evident or important. But we are talking at a length scale that is much higher. So we are going to turn this feature off and consider space to be smooth. And at the same time, as we will see later in this lecture, the radius of the electron, for example, is roughly, the classical radius is roughly 10 to the power minus 15 meters. So essentially we are not going to consider any graininess that is within the planar. And another thing to note here is that that electric field is a property of the plana. Plana is a physical thing, and electric field is a quality of the plana, and it is caused by a charged body, right? And as we have seen, this electric field goes as Q over R square. Now, we are considering these as point charges. So if I consider a point charge here, let's call it Q1, then it has a certain ability to cause electric field here, and so we call that as active charge. So indicated by A. So we're calling this as active charge. It is actively causing the electric field in the planar. So electric field from 1 that is coming from charge 1 is essentially Q1A by R square along R. So if there is another charge Q2 here, this Q2 may be receiving the action of Q1. So it is receiving the electric field caused by Q1, this one. So there, that receiving charge it is passive. It is on the receiving end. So the electric field caused by Q2 itself would be Q2 active by R square over R, but the electric field received would be by the passive charge. So if we were to take the force of charge 1 on charge 2, then that would be the passive charge times the electric field from the first charge. And the electric field from the first charge is Q1 active charge divided by R square. So what we are saying is that the ability of the charge to act and cause an electric field, we are distinguishing it from it passively receiving the electric field, because they are two different things. Action and reception are two physical things. So acting is not same as receiving. So that's why we are distinguishing explicitly between active and passive charges. So then, by the same logic, if I look at force of 2 on 1, then that would be the passive part of Q1 receiving the active electric field from E2. So I would have Q1P and Q2A by R square. But by Newton's second law, we are going to assume that there is instantaneous transmission. So we are not going to take into consideration that there may be some time required for communication between Q1 and Q2. We are going to assume instantaneous effects here. So if we do that, then by Newton's third law, these two forces should be equal. So force of 1 on 2 should be equal to force of 2 on 1, or in other words, these two things should be equal. So I can write then this as Q2 passive and Q1 active over R squared is equal to Q1 passive and Q2 active by R squared. I hope you're able to see the point here that action and reception are two different things. So we are not, we're making that distinction explicitly here. So R squares cancel, and then I can rearrange this by pulling Q1s together and Q2s together. So I would have Q1 active by Q1 passive equal to Q2 active by Q2 passive. So the active and passive charges are proportionate, and the proportionality is the same for Q1, Q2. So what we are going to do is, instead of calling these as two different charges, Q1A and Q1P, we are going to just call it as Q and absorb this proportionality constant into force. So this proportionality between active and passive charges, we are going to simply absorb that into our definition of force. And so then we can write force between two charges as simply some K, which is the proportionality constant, Q1, Q2 by R squared. So now instead of calling this Q1A, Q2P, or other way around, Q1P and Q2A, we have basically are calling them Q1 and Q2. and the proportionality between active and passive charges has been absorbed into the definition of force itself, right? So this is along R. So in Coulomb's law, we are basically looking at 2-point charges, right? And if I draw an XY axis, then I have charge 1 at R1 and charge 2 at R2, and this is the direction. Um, these are all vectors R1, R2, and this is the vector R, right? And this is Q1 and this is Q2. So then we are writing the force as KQ1 Q2 by R squared. So this proportionality between action and reception is implicitly included in that. So this K, the value of K depends upon the system of units you choose because it's a proportionality constant. And in case of CGS units, K is simply 1, where charge is measured in electrostatic units, ESU. Whereas in SI system, this K is equal to 1 over 4 pi epsilon naught. What epsilon naught means, we will see in more detail later, but this is roughly 8.988 into 10 to the power 9 Newton meter square per Coulomb square. So here we are considering in Coulomb's law that these charges are point charges, and so if they are really point charges, and if we can use these point charges we can use this approximation to put together several point charges. That is, for example, if I have Q1, Q2, Q3, Q4, and I'm interested in electric field at some point here, right? Then I can draw, from Q1 I can draw R1, from Q2 this is the point of interest P, from Q2 I can draw an R2, and from Q3 I can have an R3, and from Q4 I can have an R4, all the vectors connecting to this point P, where I'm placing a test charge. Essentially the test charge is where we are acting as if I were to place a unit positive charge here, 1 unit of positive charge here, let's say, how much force is that going to experience, and using that we are looking at the electric field here. So then electric field would simply be, for first charge it would be KQ1 by R1 square along R1 plus KQ2 by R2 square along R2, so on and so forth. So I can in general write this as K Qi by Ri square Ri. Here we have repeated the index, so it is summed over. So this is a superposition of different electric fields, right? And by superposing these electric fields from point charges, we can then construct a charge distribution of any shape. For example, if I want, I can have a charge distribution like this, and I can consider this charge distribution as if it's made up of tiny point charges, and then I can in fact take this summation of going from 1 to n kqi by Ri square Ri, right? So if I want to know the electric field from this continuous charged body at some point P here, then just like the previous example, we're dividing this volume into several tiny charges, and we're taking that volume to taking the charge to an infinitesimal point charge, and combining all the effects at point P. So if I can make this into an integral, then I would have essentially electric field would be equal to, instead of Q, we can then talk about a density of charge, rho r prime, let's say, and integrate that over V to get the overall charge, and r minus r prime square. So if I take a particular point on this continuous charge distribution, let's say here, right, then what I'm looking at is essentially from the origin to that point, that I'm calling it as r prime. So the charge density at that r prime, right? And we are going to move this point around and shift this to each different cell along the volume, right? So we're going to move that. So we're integrating over the volume. And from this point to P, the distance would be r minus r prime, where r is the distance from the origin to point P. So this vector connecting these two point P to this particular infinitesimal element would be r minus r prime. So that's how we have r minus r prime square, and the direction will be that of defined by r minus r prime. So in general, we can write the electric field for a continuous charge distribution as E equal to K times over the entire volume. The charge itself is rho of r prime divided by r minus r prime square, and r minus r prime divided by the magnitude of r minus r prime to take care of the direction, and then we're integrating it over the entire volume. So this is electric field coming from one charge, and the force this causes on another charge is Q times the electric field. So if I have a charge Q in electric field E, it experiences a force F, which is given by QE. So now with this, let's see how we can consider spherical charge distribution. So if I have a spherically symmetric charge distribution, right, a volume charge distributed on a spherically symmetric distribution, then I can consider this, I can approximate this as a point particle centered at the center of the sphere. And we can do this because we can show that electric field within the sphere at any point within the sphere should be zero. So we can instead of looking at the spherically symmetric distribution, we can take all the charge that is on the sphere and treat it as if it's a point charge situated at the center. So we can quickly show how the electric field within a spherical distribution is zero. So to this end, consider a spherically symmetric charge distribution. So let's say I have, let me draw this with a different color here. Let's say we have a spherically symmetric distribution. Then to know the field at any point r within the sphere, let's say here, then let's say we consider a slice. So let's consider a slice here of this charge distribution. Now, if I take a look at this ring of charge, this ring of charge would have a total charge of sigma 2 pi r sine theta 2 pi r squared sine theta d theta. Because if this ring is situated at let's say r1, then that's what the total charge would be if sigma is the charge density. Now, if you look at this, the effects of this ring at this point, the electric field from here would point in this direction, whereas electric field from the other side would point in this direction. So then essentially the red one would have a component this way, and the x components cancel out, and you have only the y component, or the bottom or downward component rather, surviving. So then I can write the net force from this charge as k times the charge, which is sigma 2 pi r1 square sine theta d theta. So we're considering the angle to be theta here in spherical polar coordinates. And only a cosine component of this survives. So we have cosine theta, and the distance is r1 square, and it is pointing in a way downwards at that point within the sphere. So similarly, if I consider another shell here, another ring here, that ring would exactly have the same thing, except let's say this ring is at R2, then the force from that would be sigma, or the electric field from that would be 2r2 square sine theta d theta divided by r2 square and cosine theta. But because this ring is below, it would be pointing up. So if you integrate over the sphere, then these components cancel out anywhere inside the shell. So the electric field, the net electric field, would be 0. So the net electric field is 0 in any uniformly charged shell. So for any uniformly charged shell, the electric field is 0 because of the spherical symmetry. You would have the components from the bottom half pointing up, from this pointing down, and then they all cancel out. All right. So now the question that we can ask ourselves is, if I consider these fundamental particles like electron as a sphere of charge, the question we are asking is, how much energy does it take to put together such a spherical distribution of charge like an electron, for example? So to know this, we have to start with the definition of potential energy. So when we ask ourselves how much energy does it take to put together an electron, essentially what we're saying is that, for example, let's say there are some point charges very, very far away. So this is that far away place where there are so many point charges very far away from each other. So we can neglect the mutual interaction between these point charges. And I'm assembling a spherical charge, like an electron, for example, at this point. So I'm going to bring in these point charges. Let's say I have Q1, a point charge. I'm going to bring that in and put this here. Then I'm going to bring another charge from this very far away place, Q2, and I'm going to stack these Q1, Q2, Q3, so on and so forth, so many point charges. I'm going to stack these to construct spherically symmetric distribution. So to calculate the work required to construct such a spherical shell or a sphere, to do that, let's go back and look at what potential energy is. So like in mechanics, the potential energy, here we're going to define it from infinity to R0, F dot dr. What this means is that when we say infinity, we are meaning that we are bringing these charges from a very far away place where mutual interactions between these point charges can be neglected. So it's a mental construct there, and then we are bringing that to a particular point R0. So here then we have a negative sign because we have, so I'm bringing it in this direction here, right, in the field. So I have negative sign KQ1 Q2 by R square R. So if there is Q1 here and I'm bringing in Q2, right, then the work done is in bringing Q2 is minus KQ1 Q2 by R square along R, right? There's no R, sorry. There's no R because it gets out of the dot product. So then you can integrate that, and KQ and Q2 simply come out, and you have infinity to R0, 1 over R square dr. So then you have negative KQ1 Q2, and it is going from infinity to R0, and you get a negative sign because of the integral, so you get by R0. So note that this is positive if Q1 and Q2 have the same sign. So what that means is if Q1 is positive, right, then Q2, if Q2 is also positive, then it should be naturally be repelled because both are positive charges. So it has to be pushed. It has to be pushed against that, and it has to be pushed towards charge Q1. So that's why the work done is positive there. And for opposite sign, there's a natural tendency to get attracted. So the work would be negative if Q1 and Q2 are opposite, because there would be attraction instead of repulsion, right? So now what we are going to do is we're going to calculate work done to construct a uniformly charged spherical shell. Our ultimate goal is to figure out how much energy does it take to put together an electron to construct a spherically symmetric charge distribution. So we are starting with a spherically symmetric charged shell. So you can imagine a spherically symmetric charged shell. Right, it's hard to draw this in 3 dimensions, but imagine a spherical shell. And then what we are going to consider is the spherical shell itself. We're going to consider it as shells within shells. So if I were to draw a 2D cross section, so if I were to cut this like this and chop this like this and draw a 2D cross section, then I essentially have a shell, and I'm considering that the shell is itself made up of shells, right? So if we say that the charge is distributed uniformly with linear distribution, and let's call that lambda of r, right? And then if I have a thickness dr, then the total charge in that is going to be dq is going to be lambda of r d of r. So if I go from the origin to a point, let's say r1, then or r prime, let's use the prime system here instead of 1. If I go to a distance r prime, then I would have the charge there would be lambda of r prime or dr prime, right? So we are dividing, essentially we're dividing the shells, one big shell into shells within these shells, right? So in the cross section that you see here, right? Essentially the dimension of this shell is dr, and within this dr we are considering that there are other shells that we are indicating by dr prime. So if I were to draw it out more clearly, so I'm just going to draw that out more clearly. So if I take the cross section of the shell, so this is the cross section of the shell, so this itself is dr. So it would have a charge of lambda r dr, but we're considering shells within the shells. Again, this is a 2D representation of this 3D shell. So this is 3D shell, and we're cutting it across. So we're seeing a circular cross section. So the charge in the original shell itself is lambda r dr, and then we can cut this into smaller portions. So this smaller portion here, or here, this smaller portion is dr prime. So then for that smaller portion here, this one, the charge would be lambda of r prime, where it is from the center. If it is at r prime, dr prime, right? So if I were to look at, again, I'm going to draw the shell again, the cross section of it, and so the thickness itself is dr. So the total charge is lambda r dr, and we're going to go from r minus dr by 2 to r plus dr by 2, right? So the thickness is dr. So if I want the total charge within this, then I can go from this end to that end and integrate. And so I can do that to get the total charge within this. I can go from r minus dr by 2 to r plus dr by 2, and I integrate out charge within each shell. So we're dividing this shell into tinier shells, right? And these tinier shells are what we are integrating over. So the charge within each shell is lambda of r prime dr prime. So now we can also calculate the force, effective force, because what we are trying to do is we are trying to construct from point charges. We are trying to construct a spherically symmetric charged shell. So if I take a point, for example, let's go back to the spherical shell in 3D. If I take a point here within the sphere at r, this is going to be experiencing force from what is beneath it, because as we have seen from the previous example, right, that within the shell, electric field at any point would be 0. So using that, you can see that the charge, only the charge that you put together before, in the sense that if I'm constructing these charges, so if I put Q1 and Q2 here, and I'm bringing in Q3, Q3 would only experience the effect of Q1 and Q2. So then, to figure out the total force, we integrate dF, and dF is simply E times dQ, right? And let's look at this electric field itself. This electric field itself depends upon the charges that are already there. So, so we are only interested from r minus dr2 to r prime, because only the charges that are put together, so we're putting together shell by shell, right? So we are starting from r minus dr by 2, we're putting one shell there, and then we're progressing a little bit by dr prime, and we're putting another shell there, right? So this new shell that I'm adding here, right, after following r minus dr by 2, this new shell I'm adding is only experiencing the charge beneath it, right? So then we can write the electric field from the charge beneath this dr prime as, starting from r minus dr by 2, we are going till dr prime, and the charge within it is lambda of, we're going to use another notation here, r double prime, to indicate the charge beneath dr prime. So we're going to have r double prime dr double prime by r prime square times k. So this electric field is coming from the charges that are already there. So we are assembling, essentially we are trying to assemble a spherically symmetric charge distribution. We want to figure out what is the energy in it. So to do that, we are considering that we are bringing point charges from infinity and assembling them. So to find out the total work, we have considered one shell to begin with, one spherically symmetric charged shell. And within that shell, we are looking at layers within that shell, shells within that shells. And then we are asking that if I start from r minus dr2, so I lay out a shell at r minus dr by 2, and then I progress by dr prime, and then I'm laying out another shell at r minus dr by 2 plus dr prime, right? So if I am bringing charges to lay out this shell, the charges to lay out this shell are experiencing the charges that are here. And that's why we are starting our integration between r minus dr by 2 to dr prime. And to know the charge here, we are integrating, and that gives us the total charge, and of course the distance is r prime. So now I can plug this back into electric field, and I also know what the charge is. So overall, I can then write the effective force as EdQ, and as we have seen dQ itself, right, we have seen Q as going from r minus dr by 2 to r plus dr by 2, lambda of r prime dr prime. So if we integrate over the shell going from r minus dr by 2 to r plus dr by 2 over thickness of dr, we get the total charge in the shell. So that's the charge itself, right? So then I'm going to write this as r minus dr by 2, r plus dr by 2. This is the charge in the shell, so I have lambda r dr prime. And if I start from r minus dr by 2, I lay out a shell at r minus dr by 2, then I progress by dr prime and lay out another shell at r minus dr by 2 plus dr prime. Then this shell is going to experience the electric field from whatever charges are beneath it. So that electric field is going to go from r minus dr by 2, that's the first shell, to wherever we are, and that is r prime. And here we're going to use another dummy index, dr prime, so that it's not confused with r prime. We're integrating to find out what is this charge that is producing this electric field experienced by the new point charge you're bringing to lay out a new shell at dr prime, divided by r prime square. Right? So that's what we have. So here then we can use the fundamental theorem of calculus. So the fundamental theorem of calculus is if I am integrating between r minus dr2 to r plus dr by 2, f of r prime dr prime, then we essentially are taking the average f of r dr. Right? So then by using that, I can then rewrite this. I can take out the first integral. So the first integral is this. So if I treat this entire thing as f of r prime dr prime, for the first integral I can write it out as fr dr. So I would still have this integral left, which is going from r minus dr by 2 to r now, because I'm going to replace f of r prime dr prime with f of r dr. So then I have lambda r double prime dr double prime. This doesn't matter because it's just a dummy index that we're summing over, divided by this r prime would become r. So I have r squared, and then I have the total charge. This is going to give me the total charge, and that's going to be lambda of r dr. So this lambda of r dr is the total charge. This is lambda of r dr. So this is the total charge q, and we have the constant k from the electric field. So then the net effective force would be equal to something like from here. This is q, so I have kq by r square. So I have kq by r square, and this integral term r minus dr2 or lambda r double prime dr double prime. I know this is mathematically taxing, so I am going to take a step back and re-explain it just in case you lost me. What we are trying to do is we are trying to calculate the total work done to assemble a spherical charge distribution by bringing in point charges from far away, which we are going to call as infinity. So to do that, we are first considering one shell within that charge distribution, that spherically charged distribution. We're dividing that sphere into one shell first. And this shell itself, we are dividing it into smaller shells. So if I draw a 2D cross section, I am dividing from r minus dr by 2 to r plus dr by 2. So the question we are asking is, if I have a charge here at r minus dr by 2, how much work do I have to do to move charges from infinity to lay out an extra shell here, a new shell at a distance of dr prime? And so we considered the charge within dr prime to get the electric field, and from there we were able to calculate what is the total force, because force is nothing but charge times the electric field, and this comes out to be essentially kq by r square. And if you look at this, lambda r double prime, you just integrate it into lambda r, and dr double prime, if you integrate it from this integrand, you get dr by 2. And so lambda r dr is the total charge q. So I would have kq by r square times half. So this is the net effective force that is experienced by this new shell that we are laying out at dr prime. So now if we want to calculate the work done is we know the force. So we do F dot dr, and we are bringing the charge from infinity to a particular place R0, right? Then this is going to be infinity to R0. F dot dr, F itself came out to be kq squared by r squared times dr, right? And there is a negative sign because we're moving in the opposite direction here. So then we have this to be k by 2 q squared by r0. So what is this telling us is that if I'm bringing in point charges from infinity and I'm trying to assemble them, then that work done, the energy goes as q squared. So now if I move to a sphere, a complete sphere, then imagine that we essentially brought a small charge dq to begin with, right? So initially, if I bring say only charge dq, the only work that is the work that is done on it is nothing, because it doesn't cost any energy because there are no charges to begin with. So I'm bringing the first charge in. So let's say I'm bringing the first shell in. Let's say the first shell with delta r. This is the total charge on the first shell. So I'm bringing in first shell with lambda of delta r, and laying it down, and there is no charge prior to that, so no work. But when I bring in the second shell of charge, which has a charge of delta r, so this 2 is just the index. So I laid down the first shell of charge, right? And the second shell of charge, this 2 is not multiplying delta r, it is indicating that it is the second one. It is the second shell that I am bringing in. The second shell will experience the field produced by the first shell. The first shell itself had nothing before it, so it comes free, and the second shell itself experiences a force from coming from the field of the first one. So then we can write the work done as k times the charge, the first charge that was already there, times the second charge that we are trying to put down, the second shell, lambda 2 delta r delta r. This 2 is just indicating that that it is the second shell divided by delta r. So we're laying it out at a distance of delta r. We're constructing one shell upon another shell. So now if I bring in the third shell, which is lambda 3 delta r, again, this is just the third shell index, then it will experience a combined force from the first and the second shells. So then I'll have to add a term where it is k. The charge that is already there is the first shell charge plus the charge from the second shell, right? And the charge from the third shell is going to experience that. And so on and so forth. So in general, I can write this as k, which is the constant. If I am bringing the n plus 1 shell of charge, then it's going to experience the total charge of n shells before it, which I can get as a summation of lambda of m delta r, where m is going from 1 to n. Right, this is the total charge. So 1 to small n, sorry. So this is the total charge from n charges that I put together before I'm bringing in the n plus first charge. So this n plus first charge is going to experience the field from this n charges before it. So in general, I have this, but then I have to add all these off up. So this is just for one n plus 1 charge, but I have to add the work done for each charge. So I have another summation here, and this summation is going from n is equal to 1 to n. So I'm overall bringing in n charges and putting them together to construct this shell. So overall, I have capital N charges, and each time I bring nth charge, or n plus 1th charge, each time I bring that, it is going to experience the field from n charges that I had brought before it. So that is the thing that is representing this term. And I have to compute the energy or the work done for each of these charges, starting with n is equal to 0 to n is equal to capital N. So I'm bringing in each charge. So the first charge comes free. The second charge experiences the field from the first charge. The third experiences from first and second. Fourth experiences from 1 to 3. So that's what we are encapsulating here. And I'm summing over all the charges now. So then I can write this out as an integral, right? I can convert this to an integral and this summation to an integral. And then I can simply write the work done as K, right? The charge that I am bringing in now is lambda of R dr. And the charge that's already there is 0 to R lambda of R prime dr prime divided by R. And if you essentially work it out, this comes out to be 3K by 5 Q squared by R0, where Q is the total charge. So if I want to assemble total charge Q, a sphere which has total charge of Q, so this sphere has a total charge of Q and it has a radius of R0, and I am bringing in point charges. I'm bringing in point charges Q1, Q2 till Qn from infinity, from very far away, and assembling them one by one to build this total charge of Q with a radius R0. Then the energy of that is this much. We can equate this to the rest energy, right? So the rest energy of the electron from Einstein's equation is me square, right? So let me write this as energy. So E is not electric field. So if I equate those two, the rest energy of electron, MEC squared by per electron, is roughly 5.11 times 10 to the power 5 joules per coulomb. And the charge for electron Q is 1.6 times 10 to the power 19 coulomb, right? So I have the work done, which is this per coulomb. So I can multiply this with the total charge. So I can get this work done here. And then I can estimate what R0 is. And from this, R0 essentially comes out to be 3 by 5 K. Q for electron is E. So E squared by MEC squared. This is roughly 10 to the power 5 minus 15 meters. So that is the classical radius of an electron. And as we have seen, the graininess of space becomes evident around 10 to the power minus 35 meters. So for this electron, it's much 10 to the power 20 times different than the graininess in planar to see the difference, right? So we'll stop here, and then in the next lecture we'll go deeper into Gauss's law. Thank you.